He kōna I purangi tēnei nā te reo irirangi o Aotearoa.
They say life is stranger than fiction.
This was evidence that particles behave as waves. It's been done lots of times, so we're very sure about this. You just have to have the slits close enough together relative to the wavelength of the particular particle.
But sometimes what we see in movies or read in books is so incredible that it obviously couldn't be possible. Or could it?
Most of the time we can describe the world using classical physics because a lot of that quantum detail kind of gets averaged out and we end up working with a macroscopic description where a lot of that really just doesn't matter.
Welcome to Sci-Fi Sci-Fact. I'm Brian Crump and this is a podcast where we take science fiction's strangest ideas, weirdest elements, most unfeasible plot drivers and explore if they could actually happen in real life. Maybe they already have. And in every episode, we bring in a scientist from New Zealand's MacDiarmid Institute to explain the theories behind some of fiction's more fantastic flights of fancy. If any theory exists.
What's happening?
Evelyn, I'm not your husband. I'm another version of him from another universe. I'm here because we need your help.
Very busy today. No time to help you.
Across the multiverse, I've seen thousands of Evelyns. You can access all of their memories, their emotions, even their skills. There's a great evil spreading throughout the Multiverses. And you may be our only chance of stopping it.
Everything, Everywhere, all at once. It's a movie, and it deals with the, among other things, one of its main plot drivers is the idea of the multiverse. And here to tease out what's plausible from that is Professor Nicola Gaston, MacDiarmid Institute co-director and Professor of Physics at Auckland University. With that job title, you'd need a multiverse, wouldn't you, Nicola?
Kia ora, Brian. I manage without for the most part.
You do, but only because you've got a big brain.
Oh, I don't know. It's a matter of juggling, I think.
Yeah. Now, the multiverse. I was just looking at the premise for the movie. An absurdist comedy drama came out of the States. It seems like the beginning is that there's some person who runs a laundry, and they're in a little bit of trouble with the Inland Revenue Service, and then somehow this laundry owner connects with a parallel universe version of herself, and somehow she is the key to saving creation, saving all the multiverses from some evil thing. How's that for a summary?
That's pretty much right, Brian. I did think when we started talking about this, we should probably try to avoid any spoilers, but I think that's about as much as people would get from the trailer.
I wasn't going to say anything more than that.
But yes, no, I mean, the one key thing is that the star of the show is Michelle Yeoh, who is amazing in the role. And that is part of why I particularly enjoyed it. She does sort of come across in this initial interview with the American version of Inland Revenue as somebody who is a bit, interested in everything, but it almost portrays her as somebody who's a failure at everything, but only just, which is part of the cool part of the narrative as the story goes on, that she is close enough to being able to pick up all these different skills from her replicas in other verses.
The idea that there might be more than one universe, more than one version of whatever it is that we are in, because we struggle enough explaining what we're in, let alone explaining, although isn't that the reason for the multiverse? It's a way of explaining how things work in this one? I
don't know. That's probably a stronger statement than I would make about it. I certainly agree that we don't understand everything about this particular universe, but the idea of different parallel worlds, I think, is something that is a concept that has a longish history, but not particularly scientific, maybe more philosophical. But the scientific history of the multiverse, or of many worlds, really comes out of quantum mechanics and the development of that, and trying to understand how the probabilities inherent to the way that we do quantum mechanics can be interpreted.
Which means we're going to have to dive into a bit of a refresher on quantum mechanics now, Nicola. What is it about quantum mechanics that somehow gets solved by there being more than one of this?
Yeah, so quantum mechanics is the classical. I probably shouldn't talk about classical experiments in quantum mechanics, because mixing my classical and quantum physics will confuse people. But the traditional experiment.
It's all right, we're already confused, Nicola.
This is probably normal, given the topic that we're talking about. I'm sure there's a version of you somewhere that is not confused, Brian. And there's a version of me in some universe that is going to explain this perfectly. So I don't need to feel bad if I get it a little bit fuddled. But the traditional experiment that we go back to is when we talk about the superposition of states. So there's this double slit experiment through which you can imagine sending particles. So two slits in a wall, and you can imagine the particle could either go through the one on the left or the one on the right. But what was discovered, and this was after people had figured out that light was made of particles called photons. That was sort of the first piece of evidence that particles and waves are not mutually exclusive things. But then this double slit experiment was done with electrons, so things that we know behave as particles in some ways. But by sending them through these two slits, you could find a pattern on the wall beyond the two slits that showed that you had a wave going through one of them and a wave going through the other, and those waves interfered with each other on the far wall. And so this was evidence that particles behave as waves. It's been done lots of times, so we're very sure about this. And you get this interference pattern, you just have to have the slits close enough together relative to the wavelength of the particular particle. And so, we know that particles can behave as waves. What gets really interesting, though, there's probably two things, is that you can dial down the intensity of your beam of particles so that you know that only one of them is going through at a time, and you still get this interference pattern. So it's not that they interfere with each other, it's that a single particle has to be able to go through two slits at the same time as a wave and interfere with itself on the far side. So that's the first thing that's particularly weird. And then the second thing, which is where this whole idea of the multiverse comes from, is that if you think, but I'm not going to put up with this quantum behavior, I want to figure out whether it went through the left-hand slit or the right-hand slit, and you put a little detector there, a little camera, some way of figuring out which one it went through, then by doing that, you will stop observing the interference pattern on the far wall. And so by measuring the behavior of the particle, you are making it behave purely as a particle, and you lose that wave-like behavior. So that's sort of the complicated original experiment that has been performed many times with different types of particles, different types of wavelengths. And they don't have to be fundamental particles. You can have molecules, and the slit experiment has been done with relatively large molecules, even up to sort of 50 or so atoms, and you can still see these superposition patterns. And so this wave-like behavior is very confusing, and it sort of takes you into an interpretation of quantum mechanics that's about why is it going through both slits at once? And why do we measure it on the far wall, nonetheless, as a particular point, so as a particle that hits the wall, even though the pattern that's formed tells us that there's a probabilistic interpretation that determines the overall pattern. And so that duality of particle and wave nature can only be explained if you say that once you observe where the particle actually hits the wall, you are collapsing its wave function so that you're only you're only observing one side of what was originally probable, and you're losing sort of information about what had previously been possible for that particle.
And of course, this is mind-boggling because, we're brought up to understand that when we observe, that's all we do. I'm looking at this microphone right now. Looking at this microphone doesn't change its nature, as far as I know. Looking at this computer screen doesn't change its nature. Looking at you doesn't change its nature. Why should it be that when I look at a subatomic particle, it changes its nature?
Well, that's a really good question. And it's central to what we still struggle with, I think, in quantum mechanics, in explaining it, why it's something that often comes across as rather weird. But in essence, there are different interpretations, and I'll be careful to try and call them interpretations of quantum mechanics. They're not what we'd refer to as theories in science, whereas a theory, you sort of have evidence to say it's one way or another, or this realistic proposition of having evidence for one theory or another. Interpretations of quantum mechanics are a bit more fuzzy. So there's the original sort of Copenhagen interpretation, which goes back to Niels Bohr, who was the one who invented the Bohr model of the atoms, the first kind of quasi-quantum model of an atom. And the interpretation of quantum mechanics then was that, there is no, independent quantum world, that physics is not really about telling us how nature is, but simply what we can say about nature. And so that's a very limited view of what physics can do and how we can understand quantum mechanics. It's quite uncomfortable for scientists who are used to wanting some mechanistic understanding of what's actually happened in order to cause a particular outcome. But if you just take the probabilities, that probabilistic interpretation of quantum mechanics, that two things are possible until we make a measurement, and then we can say that one or the other thing has happened. If we just take those probabilities as all that we know, then we end up with that sort of somewhat dissatisfying interpretation. The opposite interpretation, I say this just to try and contrast the two, because I think that might be helpful, is what we call the many worlds interpretation. And this sort of came along later because that very, that probabilistic interpretation, the Copenhagen interpretation, is physically kind of dissatisfying. And so what people said was, well, actually, when the wave function collapses and you're observing a thing and it's only the one part of the wave function that is then going forward in time, if that makes sense, and the rest of what could have been possible is no longer possible, that what we call wave function collapse is sort of a bifurcation of probabilities, that in one universe, this one that we're in, this thing that we've observed has happened, and that other information in the wave function has gone on to lead to that other outcome in a different universe. And so at each moment that we measure something or observe something, this interpretation says we then have the creation effectively of a new universe in which that other probability becomes what actually happened.
Okay, let's see if I've got my brain around this. So the Copenhagen explanation is what we're dealing with here is a set of possibilities of which we will observe one or the other. It might be more than one or the other, but it's possible. There's all these possible things we might observe, and, well, we're not going to observe both. We're going to observe one or the other. Hence the fact that we see one or the other, even though if we look at it further back, we see both happening at the same time. But if we try to pinpoint it, we can't. Whereas the multi-universe is saying they're happening. It's just that the thing we can't see is happening somewhere else when we try to observe it. How close is that to what you were just saying, Nicola?
I think that was very good, Brian. I think it was at least as good as what I said, even if it was somewhat incomplete. One of the things to say is that are different versions of the many worlds interpretation. So we don't need to get too detailed about it, but the two distinct concepts and the idea that the multiverse comes out of this many worlds interpretation is the key thing here, I think.
But why would, again, our attempt to observe something at the subatomic level lead to part of this wave or particle going to another universe? And what happens in this other universe? Does it pop up because we made it pop up somewhere else?
Well, I think the idea is that the other universe is kind of spun out of the previous universe. So it's not necessarily saying that all the universes have always existed, but at each moment that an observation is made or a measurement is made, and what we actually mean when we talk about a measurement is almost anything that would lead to a wave function, to a complex quantum state being resolved into a simple quantum state. And so that's pretty much, on the scale of every time molecules in our bodies interact with each other. So it's something that happens all the time at a very small scale. And so one of the interesting things about that, comparing it to the fictional representation of multiverses, is that it's a really common thing. And it's very much about individual atoms and molecules interacting with each other. It's not really about human choices. But of course, to make sense of it, the multiverse is usually portrayed in this with this very direct connection to human choices, the paths taken or not taken throughout our lives.
Because I'm thinking, is this kind of bits of me disappearing off into another universe as you and I have this conversation, are bits of you? Or is it only when we try to observe them that we get this experience, we get this data coming back at us?
Yeah, no, so it is, I guess the observation is very much just about any interaction that then sets a quantum state into a defined state. So, when I say molecules interacting, I'm trying to think of a better way of explaining that. But so one of the funny things in Everything, Everywhere, All at Once is that there they very much set up the interaction between multiverses as a shifting of consciousness between verses. So the heroine the heroine is first of all in another verse, the person who figured out how to transfer consciousness between verses, and then she can sort of tap in to another verse to experience that world. And so it's really about shifting consciousness. And that's maybe better than some versions of the multiverse that I've seen in fiction. There is a movie that also just came out this year, which is called Multiverse.
There's another one of me, and there is another one of you. That, my friend, is the key to survival.
I was kind of interested in how different the conceptions would be, and this possibly answers your question. So in the movie Multiverse, there's the set of 4 physics students trying to set up this transfer or transfer between verses. And in their version, they actually managed to transfer full people and even a goldfish between verses. And then they sort of get into quite a dark, I won't sort of unpack the plot too much, but they get into quite a dark position where they start talking about instability created by the same person having 2 copies in the same world, and that the verse cannot sustain 2 versions of the same mass, and therefore one of each person has to die in order for space-time to heal itself, which I don't know. I didn't find that as convincing. I think the portrayal in Everything, Everywhere, All at Once, where it's the consciousness shifting, is at least a little bit more, or at least a little bit less problematic.
Well, when quantum physicists talk about multiverses, are they talking in terms of there being an infinite number of the thing that we're in right now? Or is it quite a different thing? Could every different universe behave in a completely different way, and that this is the only one where you and I have conversations like this?
So yes, they can have quite different setups, but the idea is that there should be a lot of them very close together, because these quantum measurements are just so ubiquitous that they're happening all the time. And so there should be versions of our world in which the same conversation is happening, but just very slightly differently. But then there might be versions of the same world where we both exist, but something very different happened many years ago, so that the basis of our world is quite different. And so they did actually try and do that quite nicely in Everything Everywhere All at Once, where there's one of the worlds that she manages to visit has an evolutionary branching, presumably a long way back in time, and yet the two protagonists who meet in that version of the world are nonetheless very similar people. So the problem with the idea, and the real problem with the idea that I have, is that everything being possible eventually just leads you to a position of nothing really mattering. It becomes quite, if there were more constraints on what was possible, I think it would be a more pragmatic idea. But absolutely everything being possible, it just, I struggle with that.
A point in every direction is the same as no point at all.
Well, yes.
Which is what they say in one of my favourite kids' movies, The Point, by Harry Nielsen. I don't know why I thought of that, but I just did. Now I've lost my train of thought. That was a silly thing to do. Look, is it possible that when we try to make these observations of quantum data or quantum subatomic things happening, and in doing so, part of what's going on disappears into another universe, shouldn't we then expect things to just appear in ours as they're sent to us from another parallel universe? And is there any evidence that things turn up?
No, so it's not quite like that. It's more that there is a different universe created at each branching point. So there is a sort of a forward sense in which, at the point that a wave function collapses, a new universe is created.
Creates what, like another Big Bang?
No, I don't even know how to. It's just something that happens in the same physical space, but it's parallel to us. Is the best concept I can have of it, really. So it's not suggesting it's going to struggle with trying to say something sensible about the physical structure of the universe, Brian. So it's not so much that there's a Big Bang, but that there's a divergence, that there must be a replica of everything in this universe, but where that particular small quantum measurement has been made, a small divergence happens at that point that then unfolds and leads that different parallel universe down a different pathway.
Given the number of possible quantum things that have happened so far in the history of this universe, there must be trillions, gazillions of other universes by now.
Well, the only way to think about it is that they're infinite. There's no other number that makes sense. And, infinity is sufficient for what we're talking about. But it's also entirely impossible to get our heads around, right?
Don't they take energy?
Yes,
somebody in the background.
The idea that we only get more universes out and that they don't somehow die off is something that troubles me, Brian. But I think we have to remind ourselves that this is just an interpretation, an explanation driven by taking the mathematics seriously and saying, well, what does that mean? You can either go down the one pathway of just saying, well, it's about probabilities and we can't know exactly what's happening and we shouldn't worry about it. Or, at this other end of the scale, we can have this this concept of there being many worlds, and some people seem to find that a more satisfying explanation.
I mean, it's obviously a great little possible plot narrative for a movie or a story, and there have been quite a few of same characters, alternate outcomes.
Have you ever wondered what might have been? Would things be different if you caught the train instead of missing it?
Sliding Doors comes to mind, even Back to the Future. I mean, they go back and then they muck up time and then they have to go back and fix it. They have to go back to the future, back to even further into the past. And they've got, the idea is that you now got these different outcomes created by time travel. I don't know if that's the same thing that we're talking about here, is it though, Nicola?
No, I think time travel is different, or at least how it fits into, scientific descriptions. It's a bit different, but there are absolute parallels in the way, and certainly in the way it's dealt with in fiction, and definitely the idea in this movie Multiverse that having two versions of the same person in the same place would break space-time in some way. I partly just didn't find that convincing because, we're composed of atoms, sure, but all our atoms get recycled over the course of our lives. So I sort of figure if the universe is even slightly different, then we should be a little bit different in the composition. So the
multiverse actually as a satisfying or satisfactory explanation for some of the vagaries and mysteries of quantum mechanics. How much work is there to be done, Nicola? Does it really do what it intends to do? I mean, what I'm really saying, Nicola, is does it convince you? Do you think it's the most likely explanation for what we observe?
So I have a couple of problems with the many worlds interpretation. I think one is maybe more philosophical, and that's just that it's quite a nihilistic way of viewing the world. And I think this was something that Everything Everywhere All at Once actually comes out with quite brilliantly. By the end of the film, it really does get across the idea that the issues that the characters are having are created by this impossibility of holding all these different possibilities in their minds at the same time, that is enough to drive somebody mad, really. And yet that if everything can happen and everything does happen, that can lead to a certain fatalism, but a very negative fatalism, that nothing that you do actually matters, because in some version of the multiverse, a better outcome came about. One of the philosophical objections to the multiverse is that you could sort of suggest that playing a form of quantum Russian roulette was a sensible thing to do, because you'll win in one multiverse, and in any verse in which you lose, it doesn't matter, right? And so that inevitable negativity or fatalism is one reason I think as a construct it doesn't perhaps lead us anywhere particularly useful. That's probably my biggest personal objection. That's not particularly scientific. I don't think it's particularly helpful in how we think about things.
In terms of the science, however, how do you rate that?
In terms of the science, again, I think one of the things is that actually, that's a good question. So it comes back to similar objections that I have to actually thinking about time travel or teleportation, where there are examples of using quantum physics to look at the way that we move information about through entanglement, for example, And so there are a lot of these things that we can do at a very small scale with individual particles under very controlled conditions. But once we get to the macroscopic world, we know that all these quantum particles interact with each other quite strongly in complicated ways. And that's what causes this kind of wave function collapse that means we lose information from the wave function. And we know actually that most of the time we can describe the world using classical physics, because if you like, a lot of that quantum detail kind of gets averaged out, and we end up working with a macroscopic description where a lot of that really just doesn't matter. So to me, the idea that those interactions between quantum particles that are happening all the time, and that there are so very many of, that they somehow have this much more consequential importance. I don't know. I guess I find that a little bit dissatisfying. It's at least as dissatisfying as the Copenhagen interpretation, even if that is itself also a bit dissatisfying.
I mean, the thing is, it works. Like, I hit the table, I hit it. It's there, it's solid. And I know that what I've just done is use my fist, which is made up of mostly nothing, to hit a table which is made up of mostly nothing. But still, because of all the other things that go on, the forces that hold together and force apart various atoms, means that I get that sensation. Makes sense. And so it doesn't really, as you say, it doesn't matter whether there's all sorts of stuff going on at the quantum level that doesn't make sense if, as you say, it averages out into the atomic world and does.
It's interesting because it's actually a big part of my research area is to use quantum mechanics, Schrodinger's equation, to describe the interactions between atoms and to predict the properties of materials, how they interact with light, how conductive they are, what sort of structures they have, how the atoms like to arrange themselves. So I'm quite attached, I suppose, to quantum mechanics being a very practical theory. And I do think we possibly overemphasize the weird aspects of it when we come from this original background of wave-particle duality, where we sort of teach quantum mechanics by first having taught classical physics and then explaining all the ways in which classical physics doesn't apply to particles. For the most part, that still seems to be the way that we're most comfortable teaching it. But I think one of the most interesting things in research being done into quantum mechanics is to try to understand whether there'd be a better way of approaching the problem, whether starting from this behavior of particles and they have these complex wave functions which describe the different things that they can do is the right way of thinking about it, or whether we should come from a different perspective. Increasingly, people talk a bit more about the information being what is processed in quantum mechanics rather than the movement of particles, which is a very classical physics-based conception of what's going on.
Nicola, was one of the things that led us into this quantum world, apart from the remarkable experiments that were carried out that came back with these remarkable observations, that scientists were trying to work out, well, what happens when, say, I'm looking at the lights right now in the studio. Wasn't it the way that the wires glow and create light one of the things that people were trying to explain when they became entangled in the quantum world? Wasn't it?
When they became entangled, yes. Slowly entangled. It's got a bit of a longish history. It was Planck, Max Planck, who was studying black body radiation, so the full spectrum of radiation and why it has a particular set of frequencies or wavelengths, and just trying to fit that spectrum, what we see coming from the sun, for example, to what we knew about heat and the generation of light. Didn't work until he came up with this little constant, which is called Planck's constant. And that's exactly what then produced the ability for Bohr to create his model of the atom, which had fixed orbits, quantized orbits, And that was based on Rutherford's discovery of the nucleus with the gold foil experiment, which most New Zealanders have heard about because we are rather proud of Rutherford. And that same Planck's constant is then what was used to describe this wave-particle duality. And that was by saying, well, okay, we can find these photons. So this is the work of Planck to say that effectively, if we have to scale the energies of or limit the energies of light to represent the spectrum of black body radiation, then we can turn that around and say, well, all particles must have a wavelength. And so one of the interesting things about that is it's what we call the de Broglie wavelength of a particle. And you have a de Broglie wavelength, Brian, and so do I, if we think in quantum mechanical terms. So we can all behave in quantum mechanical ways, but only if our wave functions are able to interact with each other. And so the cool thing about the de Broglie wavelength is that you can calculate it by dividing Planck's constant, which is this very small number that we call h, by the momentum of something. And so the momentum is just its mass and its speed multiplied by each other. And so what that means is that when you have something very, very small, like an electron or an atom, or even some number of atoms, they all have wavelengths that are much larger than their size. So they primarily interact through their wave functions. But when you're a person and you divide through by the momentum that we have, this very small number divided through by that, you find that actually you have a very, very small wavelength. And so our wavelengths would be much smaller than the size of an atom. And so we would never interact through our wave functions. But you could calculate one.
That sounds like a whole new platform right there to jump off into another sci-fi kind of world.
James T. Kirk.
Excuse me?
How did you find me?
How did you know my name?
I have been and always shall be your friend.
Look, I don't know you.
I am Spock.
Bullshit.
There's a couple of questions to finish with. One is it likely, Nicola, that somebody eventually will come up with something else, not the Copenhagen probability thing, not the multiverse, something else that explains what's going on?
Yes, I would be optimistic and say that we can probably do better with interpretations of quantum theory than what we have at the moment. It is...
But that's interesting, though. You've used that word again, interpretations, because this is my last question, and that is, we're dealing with observing things that are, smaller than the wavelength of light, aren't we? And therefore, we can never see them. Never. Because they can't be seen, because they're smaller than a wavelength of light. And is it possible that there's a whole swathe of stuff that's smaller than a wavelength of light that we will never see and can only ever interpret?
There is, but I would just say that it's not so much about what we can see, because we can observe quite directly things that have smaller wavelengths through using electrons, for example, rather than photons. There are lots of tricks we can use to observe smaller and smaller and smaller things. So we can observe even quite directly the structure of molecules at the atomic scale. We can observe electronic orbitals to some extent. We can absolutely observe the energies, by which I mean, by observing, I just mean measure the energies of subatomic particles, right? So we have access to a lot more information about quantum particles. But what we still, I think that the key thing that we really don't understand beyond knowing that it's real is the role of probabilities in the way we deal with quantum mechanics. And that's why, for the moment, we have interpretations, and there's plenty of room for argument about them. And yeah, I do think that grappling with this underlying theory, and on the one hand, it's a very academic exercise, and the practical position of just saying quantum mechanics works and we should use it because that's helpful is the one that I tend to employ in my own research. But I do think there's space for thinking about why and how these things happen. And so, yeah, I think there's still lots to learn.
Nicola, it's been fantastic talking with you. Thanks so much for your time.
Thanks, Brian.
Thanks for listening to this episode of Sci-Fi Sci-Fact, hosted by me, Brian Crump, produced by Andrew Robertson, and of course, made possible thanks to the incredible knowledge of those brilliant scientists at the MacDiarmid Institute. You can find more episodes of Sci-Fi Sci-Fact on the RNZ podcast page. RNZ podcasts are also available on Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or pretty much wherever you might find your podcasts. And make sure to follow us so you don't miss out on any new episodes.